Swayam Prabha. Digital India. Educated India.
Welcome back to real time digital signal processing course. So, today we will discuss discrete Fourier transform in detail. So, coming to the previous class, so we covered FIR and IR filters in the previous module. So, we saw how quantization affects the frequency response for the IAR filter, and then how we have to do the scaling and other parameters what we have to take it into consideration to design our IAR filter. So, coming to now we will go to the frequency domain. Why we have to go to the frequency domain? So, first of all what we have to say, from analog time domain we have to move to frequency. So, the time domain, the components which we are unable to see basically. So, whether the other domain, that is in the transform domain, which is going to give us the parameters what we are looking for. So, for that we go to the Fourier domain basically, that is frequency domain. So, in this case today we will be discussing about discrete time Fourier transform first, and then we will see that how discrete Fourier transform the thing is developed. So, in that is what we are going to tell, that is we introduce the discrete time Fourier transform for the theoretical analysis of our discrete time signals and systems, and the discrete Fourier transform which can be computed by our digital hardware for practical applications. So, coming to the definition, so we know that discrete time Fourier transform Dtft is for the discrete time signal, x of nt is defined with this equation, that is x of omega is equal to sigma n is equal to minus infinity to infinity x of nt into e power minus j omega nt, and we say x of omega is periodic function with period pi. So, the frequency range of discrete time signal is unique over the range, that is minus pi to pi, or we can consider 0 to 2 pi. So, Dtft of our x of nt can also be defined using the normalized frequency. So, if we take that, then it is going to be x of f, which is equal to n is equal to minus infinity to infinity x of nt into e power minus j 2 pi n capital F into n, where our f is frequency is given by omega by pi, which is nothing but f by fs by 2. F is the signal what we are interested in, and fs is the sampling frequency. So, we say that normalized digital frequency in cycles per sample. So, how we are going to represent the spectrum of discrete time signal? So, we said that it is periodic sampling imposes relationship between independent variables t and n, as t is equal to nt, which is nothing but n divided by fs. So, that we can show that x of f is equal to 1 by t, k is equal to minus infinity to infinity, x of f minus k into fs. So, we will be seeing that x of f is the sum of the infinite number of x of f, what we are going to say, which is the Fourier transform of our analog signal x of t. It is scaled by 1 by t, and then frequency shifted to k times fs. So, it also states that x of f is a periodic function with period t is equal to 1 by fs. So, we will be seeing the spectrum here. This is our x of f, what we are considering it, and this is the maximum frequency in our input signal. It varies between minus fm to fm, and then f is the x axis. So, coming to the next one, if why we are going to have the replication, that is discrete time signal caused by sampling basically. So, this sampling extends original spectrum whatever we have considered x of f repeatedly on both sides. So, we will be seeing this is extended on both sides. So, we call this as minus fs by 2 and then fs by 2. So, we will be getting the images of the spectrum basically. So, what happens if our maximum frequency is less than or equal to or half the sampling frequency according to Shannon sampling theorem. So, then what happens? So, we will not be seeing any overlap in the thing. So, that is what the theory says, that our FM is going to be much away from our Fs by 2. So, in the next case, if Fm is what we say is more than our Fs by 2 or Fs sampling frequency is less than twice the maximum frequency component present in our signal, then what we are going to have is we will be seeing the overlap of it. So, Fs by 2 is here, minus Fs by 2 is here, or Fm has more than Fs by 2. So, you will be seeing that we will be getting the earliest signal. So, this we may not be able to reconstruct to the original signal, it may map it to some other signal as we have seen earlier sync in our sine wave generation also. Coming to discrete Fourier transform. So, what we have is this is we call it as a finite duration, whereas Dtft was discrete in time, but frequency was continuous in omega. Here both frequency and then time have been discretized. So, x of n of length in is defined as given by x of k. So, n is equal to 0 to n minus 1, x of n into e power minus j 2 pi by n into k into n. K will be varying 0 to n minus 1, and then we will be seeing that n is varying 0 to n minus 1. So, we call k is the frequency index. So, we will be saying x of k is the kth Dft coefficient. The summation bounds reflect the assumption that x of n is equal to 0 outside the range 0 to 0 less than or n, which is less than or equal to n minus 1. So, we call Dft, that is n samples of Dtft of x of omega over the interval omega in between 0 and then 2 pi at n equally spaced discrete frequencies, that is omega k, what we call it 2 pi k by n. Here k is going to be 0 to n minus 1, and the space between two successive x of k is nothing but 2 pi by n. We call it as a resolution of the Dft. So, we say the unit for this is radians, and then if we represent in terms of sampling frequency, it is going to be Fs by n hertz. So, then what we can see that as an example, if the signal n is real valued and n is even number. So, we can show that x of 0 if we substitute, that is n is equal to 0 to n minus 1, which is nothing but x of n into e power minus j 0, which is nothing but x of n, and then x of n by 2, any other n divided by 2 is represented as this way, n is equal to 0 n minus 1 e power minus j pi n into x of n. So, this is we know that e power minus j pi n is nothing but minus 1 to the power of n into x of n. So, what we observe from this is the DFT coefficients x of 0 and x of n by 2 are real valued. That means, if x of n is real valued, then output even the DFT coefficients are real valued. So, if n is an odd number, x of 0 is still a real, but x of n by 2 is not available. Now, we will consider the sequence or signal of finite length, which is given by x of n is equal to a power n. N is varying between 0 to n minus 1, and then a is in between 0 and 1. Then DFT of x of n is computed as, that is x of k, substitute x of n with a power n, and then we have e power minus j 2 pi k by n into n. So, by simplifying, so what we will be getting is 1 minus a to the power of n by 1 minus e power minus j 2 pi k by n, and k is going to vary between 0 to n minus 1. So, we can represent this DFT as W n k, we call this as the Twiddle factor, which is given as e power minus j 2 pi k by n into k n. So, we know that we can split our exponential into cos and sin function. So, cos 2 pi k n by n, which is real, and then minus j sin 2 pi k by n is the imaginary part. Both k and n will be varying between 0 to n minus 1. So, then if we substitute W and k in our equation, so x of k will be equal to n is equal to 0 to n minus 1 x of n into W n k n, k is varying between 0 to n minus 1. So, that is what I said, Twiddle factors of DFT, W n k n are called, and then we know that n roots of unity is a clockwise direction on the unit circle. We will see it in a while, hold on. So, then what we call W n, n is nothing but e power minus j 2 pi, which is equal to 1, which is nothing but equal to W n 0. So, we can see that the DFT is periodic in nature. So, that is the reason why we take 0 to n minus 1 when we substitute x of n is equal to n basically, that is n is n, then what happens, kr n becomes n, it becomes e power minus j 2 pi, which is 1, which is nothing but W n 0. So, and then the center point, what we will check it up, W n, that is n by 2, which is equal to e power minus j pi, so which is nothing but minus 1, and W n k, what we call it between the other values as k is equal to 0 to n minus 1. So, if we extract the symmetry property, then what happens? We can split this into two parts, that is W n k plus n by 2, which is equal to minus W n k. So, k is in between 0 to n by 2 minus 1, and if we consider the periodicity property, then what happens? W n k plus n is nothing but W n k. So, we know that the inverse discrete Fourier transform, we call it as IDFT. So, is used to transform the frequency domain coefficients x of k back to time domain signal x of n. The IDFT is defined with this equation, x of n is equal to 1 by n, k is equal to 0 to n minus 1, x of k into e power j 2 pi by n into k n. So, if we represent with Twiddle factor, it will be 1 by n into k is equal to 0 to n minus 1 x of k into W n minus k n, in this case n will be varying between 0 to n minus 1. So, we can see that how the Twiddle factors of DFT in case of n is equal to 8 is assumed. So, on a unit circle. So, we will be seeing that this is W 80, which is equal to 1, and then what we have is W 81, and then W82, W83, and then n by 2 what we just now saw, that W84 which is nothing but minus W80 which is equal to minus 1, and then we know W85 is equal to minus W81, and then W86 will be equal to minus W82, and we know that when we come to W87 it comes out to be minus W83. You will be seeing that this is what it is, minus W83, and when it becomes W8 is equal to 8, just now we said Wn n is equal to Wn0, here it is W88 which is equal to W80 equal to 1. So, these are the twiddle factors. Depending on power of 2, if you are considering it, it will be on the unit circle this way, and then it is going to be repeated after a period. In this case we have assumed n is equal to 8. So, the equation now again repeated for DFT what it is shown, and then in terms of twiddle factors, W what we call it, Wn k n, where 0 is less than or equal to k, and then n is less than or equal to n minus 1, both k and then n are in 0 to n minus 1. How we can write the in a matrix form, that is all these coefficients are, first row is 1 and first column is 1. After that we will have Wn 1, and then the last one in this row is Wn minus n to the power of n minus 1. So, that way what you represent it. So, last row what you can see, Wn n minus 1, Wn n minus 1 whole squared. So, just to show that how twiddle factors are represented with Wn weights, we will assume given x of n is equal to 1 1 0 0. So, I think it should be striking to your mind that here we have assumed n is equal to 4. So, we will see the DFT 4-point sequence what it is going to be. So, we represent x is equal to all 4 ones here and then 4 ones in the column, then this is W41, W42, W43 and W42, W44 and W46, so on in the last line, or you will be seeing it. When you expand them, so in terms of e power, then you will be seeing that W41 is nothing but minus j, and W42 is minus 1, and W43 is minus of W41 which is plus j. So, here also you will be seeing the thing. This is how we will enter the thing, and we have been given x of n is this value. So, this is our coefficient, and then this are our x of n. When we do the matrix multiplication, so the DFT of the sequence is nothing but 2, 1 minus j, 0 and 1 plus j. So, to see that whether our DFT is correct or not, we will take the IDFT. So, we assume that Fk is equal to k into Fs by n, k will be varying between 0 to n minus 1. So, then what happens to our x, which is nothing but 1 by 4, that is 1 by n in this case. So, we will substitute, our matrix is going to be just our DFT matrix, but you will be seeing that the twiddle factors are negative in this case. So, we will be substituting all these values. When we do that, so 1 by 4, this is our DFT coefficients in the IDFT basically. So, you will be seeing that it is a complex conjugate of this DFT coefficients, which it will be resulting in what is it, after multiplication with our x of k, that is 2, 1 minus j, 0 and 1 plus j. So, we will be getting back our x of n, that is 1 1 0 0. So, you will be seeing that this is the DFT and IDFT with an example how their what I'll call it as analysis and then synthesis equations, what we call them. So, what is the frequency resolution in this case? So, we said identical to DFT with exception of the normalizing factor 1 by n and the opposite sign of the exponent of the Twiddle factors, that is what we said. So, the DFT coefficients are equally spaced on the unit circle, we saw that. Usually we call it as the z plane at frequency intervals of fs by n, or it can be 2 pi by n, because that is what we map in the omega, that is in the frequency domain 0 to 2 pi, and then here sampling frequency is fs up to 2 pi. And we say that frequency resolution of our DFT delta is nothing but fs by n. This is the samples or the period between two samples. Frequency sample x of k represent the discrete frequency. So, where fk is given by k into fs by n for k is equal to 0 to n minus 1. So, we assume that if I do not know what is the frequency I am getting at the output, if I know the k is equal to, I will put it as 1, and we have assumed fs sampling frequency is 8 kilohertz, and then I am going to pass it through n is equal to 8 to be simpler to calculate this. Then what is the frequency fk component in this case is going to be, k is 1 and I have chosen 8 kilohertz as my fs, divided by number of samples is 8. So, then you will be seeing that fk is what I am representing at k is equal to 1 is 1 kilohertz. So, if I draw the thing, so this will be my magnitude x of e power j omega, what I can put the thing magnitude of it, and this is the fs in kilohertz what I will put it, and this is my 0, this is 1, 2, 3, I will put it as 8. So, I will be getting the peak here, which is my fk in this case what I am representing. So, this is how you will be calculating depending on k value is going from 0 to here 7 in this case. 8 will be fs by 2 point. So, it will be repeated. So, this is how you calculate, and then we know that DFT coefficients x is a complex variable. So, it can be expressed in polar form as x of k is equal to magnitude of x of k into e power j phi of k. So, this represents my phase and this represents my magnitude. So, that is how we will be representing it here, how we can compute our magnitude and phase spectrum for a given signal. So, the first is the magnitude spectrum. We will be calculating magnitude of x of k is nothing but, all of us know, real part of x of k whole squared plus imaginary part of x of k whole squared under square root. So, will give me the magnitude of x of k. And then the phase spectrum always we represent in terms of tan inverse. So, phi of k is equal to tan inverse imaginary part of x of k, real part of x of k. If your real part of x of k is greater than or equal to 0. So, if it is less than 0, then we will be seeing that it will be pi plus tan inverse of imaginary part of x of k divided by real part of x of k. So, now how we are going to represent our DFT and then Z transform? What is the relationship we will see in this slide? So, the DFT questions can be obtained by evaluating the Z transform of the length n sequences of x of n on the unit circle. We have seen it already at n equally spaced frequencies wk, which is given by 2 pi k by n, k will be varying between 0 to n minus 1. So, what is it? X of k is equal to x of z, z is equated to e power j 2 pi by n k, where k will be going from 0 to n minus 1. So, some of the terms how we will be going from one domain to the other domain, what is shown in this figure. What is it? X of t is my time domain. By doing the sampling of the signal, I will be entering into digital domain, that is x of nt. And then if I take the Laplace transform for in the time domain, then I will be going into Laplace domain, which is represented as x of s. And then how I can traverse to my digital z domain by substituting a simplest impulse invariant method, that is z is equal to e power st. I can enter into z transform basically in the digital domain, or from the digital signal I can use the z transform to calculate my x of z, and if I calculate the Fourier transform, I will be entering into the Fourier domain, that is x of omega. And then how these two are related, as you can see, by substituting z is equal to e power j omega, I can get the frequency component from z domain. Okay. So, the sum of the units and then variables and relationship and range is shown in this table. So, if we represent it as capital omega, we call it as radians per second. So, we say that capital omega will be 2 pi f, and this is the range for our capital omega, that is minus infinity to infinity, and f we call it as cycles per second in hertz. So, which is f is equal to capital F by t, which is capital F is assumed in this case as sampling frequency. As you can see, cycles per sample, that is f by fs, and then this also varies between minus infinity to infinity, and omega usually we represent it in radians per sample, and omega is equal to 2 pi f, which varies between minus pi to pi omega, or it can vary between 0 to 2 pi, and this is between minus half less than or equal to f less than or equal to half. So, this is what the relationship with respect to z transform and then Dft. So, now we will assume that how to go with we said that Dft is a periodic function. We will see how to calculate the circular convolution. So, all of you must be conversant with your linear convolution and circular convolution. Usually Dft will be represented as a circular convolution. So, we have a x of n and h of n are real valued n periodic sequences. Y of n is the circular convolution of x of n and h of n. So, which is represented as y of n is h of n into, this is the circular convolution notation what we use it with x of n, which is given as h of m into x of n minus m mod n, what we will be taking it. That means to say n minus 1 mod n non-negative modular n operation will be considering it. N is varying between 0 to n minus 1 in this case. So, how we represent in the, this is what we have in the time domain, and in the frequency domain. So, it results in the multiplication of two Fourier transform of, that is discrete Fourier transform of x and then h. So, y of k will be x of k into h of k, where k will be varying between 0 to n minus 1. So, that is what it says. If the shortest sequence must be padded with zeros in order to have the same length for computing circular convolution. So, what do we mean by that? So, x of k and h of k are of different length. So, to make them equal length, one of them have to be padded with zeros. So, we will see the linear convolution in slide 21. So, how we have padded with zeros and then made power of 2 and then used in our circular convolution. So, how we are going to compute our circular convolution? So, usually it is represented with two concentric circles, and we will be seeing that this goes in the clockwise direction. X of n and h of n are aligned actually, then we will be moving h of 0 in this direction, n minus n plus 1 and then so on, and then next last one will be h of n minus 2, h of n minus 1. Whereas you will be seeing that x of n goes in this direction anticlockwise, x of n minus n plus 1, and then we will be coming to x of n minus 2 and x of n minus 1. So, this is how we will represent. We will see with an example how we are going to compute this. So, as an example, as I have been mentioning, x of n is given as 1, 2, 3, 4 and our h of n is 1, 0, 1, 1. In this case, as you can see, both are of the same length. We will do the circular convolution. So, the steps have been written here. So, how to arrive at these steps using our concentric circles, we will see the thing. So, my x of n is 1, 2, 3, 4. It is written in this way anticlockwise, and then h of n is 1, 0, 1, 1 is in the anticlockwise. Sorry, this is in the clockwise, the x of n is in the anticlockwise. So, when I do the first time, we have aligned the x of n and then h of n together, and we multiply these two numbers, and then all of them we multiply. You will be seeing 1 into 1 is 1, 2 into 1 is 2, 0 into 4 is 0, and then here 1 into 3 is 3. So, when you add it up, this is what the step what it is given. At n is equal to 0, y of 0 is given by 1 into 1, 1 into 2 plus 1 into 3 plus 0 into 4, which gives me 6. So, then what we are going to do is I can move this as the arrow shows one step each time, my h of n in this thing, and I keep this one as it is. So, when I do that, next value is going to be 0 into 1 plus 1 into 2, 1 into 3 and 1 into 4. When add it up summation, it comes out as 9. So, this is 6987 when I do the circular convolution. So, you will be seeing that how we can implement linear convolution, just if you have done the thing. So, just I will write it here. Most of you would have used this method to compute your linear convolution. So, when I put the thing, all of us know that we put x of n, I can put it here 1, 2, 3, 4. This is 1, 0, 1, 1 what I can represent. Then I will be multiplying with the 1 into this number. This is 2, 0, 2, 2 and then 3, 0, 3, 3, 4, 0, 4, 4. So, how we are going to get the thing? So, you will be knowing that this is the way we will be adding it up and then result in the linear convolution. So, you will be seeing that this is 1, 2, 3, 7 and then 5, 7 and then 4. This is the equivalent of linear convolution. So, whereas circular convolution you can see that 6987. Can I use this method to implement linear convolution? That is what we will check in the next slide. So, you will be seeing that what we have done is we have these are the two values. So, that is for the linear convolution using circular convolution, we have to do 0 pad of L plus m minus 1 is the length of the sequence what the result is going to be. So, we have to pad both of them with these zeros, L plus m minus 1, L is the length of x of n, m is the length of h of n. In this case, we have both of them equal, 4 plus 4, 8 minus 1, 7 will be the length, what we have is 4 lengths. So, we will be padding with 3 zeros and then the other one also will be padding with 3 zeros. So, now we have, although we have the equal length, to simplify, if I want to compute power of 2, then what I have to do is I have to make them 8. As you will be seeing that 2 concentric circles I have divided into 8 parts. So, we will be putting 1, 2, 3, 4 and then 4 zeros what we will be padding instead of 3 zeros. Here also we will be doing 1, 0, 1, 1 and 4 zeros. Same way as the previous one, you can shift the thing. The resulting value with circular convolution, you will be seeing that 1, 2, 4, 7574 is achieved, which can be verified using MATLAB, or the next slide shows that how it has been implemented. So, I showed you how it has been done in the previous example. Same way, if you do the thing, you will be resulting with this value. The last one will be 0, which you can discard and then keep these L plus M minus 1 values for your result. So, you can see that we have taken little bit of DFT in to show that circular convolution property. Other properties you can look into the book and then come out with it. In the next class, we will be seeing the complexity of filtering and how we will be deriving from DFT FFT equation. Thank you.